valuable experience. Okay, today we're going to start talking about a particular class of algorithms called greedy algorithms, but we're going to do it in the context of graphs. So I want to review a little bit about graphs, which mostly you can find in the textbook in Appendix B. And so if you haven't reviewed Appendix B recently, please sit down and review Appendix B. It will pay off, especially during our take-home quiz. So just a reminder, a digraph. What's a digraph? What's that short for? Directed graph, okay? Directed graph, G equals VE, okay, has a set V of vertices, and I always get people telling me that I have one vertice. The singular is not vertice, it is vertex, okay? Plural is vertices, the singular is vertex. It's one of those weird English words. Okay, it's probably original like French or something, right? I don't know. Okay, anyway. And we have a set E, which is a subset of V cross V of edges. So that's a digraph. In an undirected graph, E contains unordered pairs. Okay. And sorry? It's Latin. It's Latin. Okay, so it's probably pretty old then in English. I guess the vertex would be a little bit of a giveaway that maybe it wasn't French. Started to be used in 1570. Okay. Okay. Good. So, okay, so the number of edges is, whether it's directed or undirected, is O of what? V squared. Good. Okay, and one of the conventions we'll have when we're dealing, once we get into graphs, we deal a lot with sets. We generally drop the vertical bar notation within O's just because it's implied. It just makes it messier. So once again, another abuse of notation. It really should be order the size of V squared, but it just messes up. I mean, it's just more stuff to write down, and you're multiplying these things and all those vertical bars. Since they don't even have a sense to the vertical bar, it gets messy. So we just drop the vertical bars there when it's in asymptotic notation. So E is order V squared, whether it's a set of pairs, because if it's a set of pairs, it's at most n choose 2, which is n squared, most n squared over 2. Here it could be at most, V squared over 2. Here it's at most V squared. And then another property sometimes comes up is if G is connected, we have another bound. Implies that the size of E is at least the size of V minus 1. Okay? So if it's connected, okay, meaning, what does it mean to have a graph that's connected? Yeah, there's a path from any vertex to any other vertex in the graph. That's what it means to be connected. Okay? So if that's the case, then the number of vertices, the number of edges, at least the number of vertices minus 1. Okay? And so what that says, so one of the things we'll get into that fact I just want to remind you is that in that case, if I look at log E, okay, log of the number of edges, that's then by this is O of log V, and by this is omega of log V. So it's equal to theta of log V. Okay, so basically the number of, in the case of a connected graph, the number of edges and the number of vertices are polynomially related, so their logs are comparable. Okay? So that's helpful just to know, because sometimes I get questions later on where people will say, oh, you showed it was log E, but you didn't show it was log V. And I have to point out that it's the same thing. Okay? Okay. So there's various ways of representing graphs in computers. And I'm just going to cover a couple of the important ones. There's actually more. We'll see some more. But so the simplest one is what's called an adjacency matrix. Adjacency matrix. The adjacency matrix of a graph G equals VE, where, for simplicity, I'll let V be the set of integers from 1 up to n, okay, is the n by n matrix A given by the ijth entry is simply 1 if the edge ij is in the edge set, and 0 if ij is not in the edge set. Okay, so simply the matrix where you say the ijth entry is 1 if it's in the matrix. So this is in some sense giving you the predicate for is there an edge from I to j. Okay, predicate, remember, is a Boolean formula that is either 0 or 1, and in this case you're saying it's 1 if there's an edge from I to j, and 0 otherwise. Okay? Sometimes you have weighted graphs, edge-weighted graphs, and then sometimes what people will do is replace this by edge weights. Okay, it'll be the weight of the edge from I to j. So let's just do an example of that, just to make sure that our intuition corresponds to our mathematical definition. So here's an example graph. Say that's our graph. So let's just draw the adjacency matrix. Okay, so this says, is there an edge from 1 to 1? The answer is no. Is there an edge from 1 to 2? Yes. Is there an edge from 1 to 3? Here. Yep. Is there an edge from 1 to 4? No. Is there an edge from 2 to 1? No. 2 to 2? No. 2 to 3? Yes. 2 to 4? No. No edges going out of 3. Edge from 4 to 3, and that's it. So that's the adjacency matrix for this particular graph. Okay? And so I can represent a graph as this adjacency matrix. Okay? When I represent it in this way, how much storage do I need? Okay, n squared or v squared, because the size is same thing, or v squared storage. Okay, and that's what we call a dense representation. Okay, it works well when the graph is dense. So the graph is dense if the number of edges is close to all of the edges possible. Okay? Then this is a good representation. But for many types of graphs, the number of edges is much less than the possible number of edges, in which case we say the graph is sparse. Can somebody give me an example of a sparse graph? A class of graphs. So I want a class of graphs that as n grows, the number of edges in the graph doesn't grow as the square, but grows rather as something much smaller. A linked list, so a chain. Okay, if you look at it from a graph theoretically, is a perfectly good example. Only n edges in the chain, okay, for a chain of length n. So therefore, the number of edges would be order v, and in particular, you'd only have one edge per row here. What other graphs are sparse? Yeah.
You could use a graph of a map where the edges are ordered.
Good. A planar graph, a graph that can be drawn in the plane. Turns out that if it has v vertices, and v is at least 3, then it has at most 3v minus 6 edges. So it turns out that's order v edges again. What's another example of a graph, common graph?
Binary tree.
Yeah, binary tree, or even actually any tree. You know, what's called a free tree, if you read the appendix. Okay, a tree that just is a connected graph that has no cycles. Okay, is another example. What's an example of a graph that's dense?
A complete graph.
Complete graph, that's the, okay, it's all ones. Okay, or if you have edge weights, it would be completely filled in matrix. Okay, good. So this is good for a dense representation, but sometimes you want to have a sparse representation so that we don't have to spend v squared space, okay, to deal with all of the where most of it's going to be zeros. Okay, it's sort of like if we know it's 0, why bother representing that it's 0? So one such representation is an adjacency list representation. So the adjacency list of a given vertex is the list which we denote by ADJ of V, of vertices adjacent to V. Okay, just in terms by their terminology, vertices are adjacent, but edges are incident on vertices. Okay, so there's incidence is a relation between a vertex and an edge. Adjacency is a relation between two vertices. Okay, that's just the language. Why they use two different terms, I don't know, but that's what they do. Okay. So in this graph, for example, the adjacency list for vertex 1 is just the list or the set of 2, 3, because 1 has, going out of 1 are edges to 2 and 3. The adjacency list for 2 is just 3. For 3, it's the empty set, and for 4, it is 3. Okay, so that's the representation. Now, if we want to figure out how much storage is required for this representation, okay, we need to understand how long the adjacency list is. So what is the length of an adjacency list of a vertex V? What name do we give to that? It's the degree. Okay? So in an undirected graph, we call it the degree of the vertex. This is undirected. Okay? In a Put that here. Okay, so that's in an undirected case. In the directed case, okay, actually I guess the way we should do this is say this. If it's a degree, we call it the out degree for a digraph. Okay, so in a digraph we have an out degree and an in degree for each vertex. So here the in degree is 3, here the out degree is 2. Okay? So one of the important lemmas that comes up is what's called the handshaking lemma. Okay, it's one of these mathematical lemmas. And so it comes from a story. Go to a dinner party, and everybody at the dinner party shakes other people's hands. Some people may not shake anybody's hand. Some people may shake several people's hands. Okay? Nobody shakes hands with themselves. Okay? And at some point during the dinner party, the host goes around and counts up the sum of the number of hands that each person has shaken. Okay, so it says, how many did you shake? How many did you shake? How many did you shake? Adds them up, okay, and that number is guaranteed to be even. Okay, that's the handshaking lemma. Or, stated a little bit more precisely, if I take for any graph the degree of the vertex and sum them all up, that's how many hands everybody shook, okay? That's actually equal to always twice the number of edges. Okay? So why is that going to be true? Why is it going to be twice the number of edges? Yeah?
For every connection, there are 2 nodes. That's like
Yeah.
one edge, one filled with one.
Every time you put in an edge, you add 1 to the degree of each person on each end. So it's just 2 different ways of counting up the number of edges. Okay, I can go around and I can, if you imagine it, that every time I count the degree of a node, I put a mark on every edge. Then when I'm done, every edge has 2 marks on it, 1 for each end. Okay, pretty simple theorem. Okay, so what that says is that for undirected graphs, that implies that the adjacency list representation uses how much storage? Okay, at most 2e, so order e, because that's not all.
Plus the number of vertices.
Yeah, so you have to have the number of vertices plus the number of edges. Okay, whether it's directed or undirected, because I may have a graph, say, that has a whole bunch of vertices and no edges, that's still going to cost me order v. Okay, so it uses theta of v plus e storage, and it's basically the same thing asymptotically. In fact, it's easier to see in some sense for digraphs. Because for digraphs, what I do is I just add up the out degrees, and that's equal to e. Okay? If I add up the out degrees, it's equal to e. In fact, this is kind of like an amortized analysis, if you will, a bookkeeping analysis, that if I'm adding up the total number of edges, one way of doing it is accounting for it vertex by vertex. Okay, so for each vertex, I basically can, take each degree and basically each vertex look at the degree, and that allocating of a count per edge and then ending up with twice the number of edges, that's exactly an accounting type of analysis that we might do for amortized analysis. Okay? So we'll see that. So this is a sparse representation. And it's often better than an adjacency matrix. For example, you can imagine if the World Wide Web were done with an adjacency matrix, as opposed to essentially with an adjacency list type of representation. If every link on the World Wide Web, I had to say, here are the ones that I'm connected to, and here are all the ones I'm not connected to. Okay, that list of things you're not connected to for a given page would be pretty dramatically show you that there's an advantage to a sparse representation. On the other hand, one of the nice things about an adjacency matrix representation is that each edge can be represented with a single bit. Whereas typically when I'm representing things with an adjacency list representation, how many bits am I going to need to represent each adjacency? You'll need order log of v to be able to name each different vertex. Okay, the log of the number is the number of bits that I need. So there are places where this is actually a far more efficient representation. In particular, if you have a very dense graph, okay, this may be a better way of representing it. Okay, the other thing I want you to get, and we're going to see more of this in particular next week, is that that a matrix and a graph, there are two ways of looking at the same thing. Okay, and in fact, there's a lot of graph theory that represent, where you do things like multiply the adjacency matrix. Okay, and so forth. So there's a lot of commonality between graphs and matrices. A lot of mathematics that if it applies for one, it applies to the other. You have a question, or just holding your finger in the air? Okay, good. Okay, so that's all just review. Now I want to get on to today's lecture. Okay, so any questions about graphs? So this is a good time to review Appendix B. There are a lot of great properties in there, and in particular, there's a theorem that we're going to cover today, that we're going to talk about today, which is properties of trees. Trees are very special kinds of graphs. Okay, so I really want you to go and look to see what the properties are. There's, I think, something like 6 different definitions of trees that are all equivalent. Okay, and so I think a very good idea to go through and read through that theorem. We're not going to prove it in class, but really provides a very good basis for the thinking that we're going to be doing today, and we'll see more of that in the future. Okay, so today we're going to talk about minimum spanning trees. Okay, this is one of the world's most important algorithms. Okay, it is important in distributed systems. It's one of the first things that almost any distributed system tries to find is a minimum spanning tree of the nodes that happen to be alive at any point. Okay, and one of the people who developed an algorithm for this, we'll talk about this a little bit later. Okay, it was the basis of the billing system for AT&T for many, many years while it was a monopoly. Okay, so very important kind of thing, and it's got a huge number of applications. So the problem is the following. You have a connected, undirected graph, G equals VE, with an edge weight function W, which maps the edges into weights that are real numbers. And for today's lecture, we're going to make an important assumption, okay, for simplicity. The book does not make this assumption, And so I encourage you to look at the alternative presentation there, because what they do in the book is much more general, okay? But for simplicity and intuition, I'm going to make this a little bit easier. We're going to assume that all edge weights are distinct. Okay? All edge weights are distinct. So what does that mean? What does that mean that this function w, what property does the function w have if all edge weights are distinct? Who remembers their discrete math? It's injective. Okay, it's one-to-one. Okay, it's not one-to-one and onto necessarily. In fact, it'd be kind of hard to do that because that's a pretty big set. Okay, but it's one-to-one. Okay, it's injective. Okay, so that's what we're going to assume for simplicity. Okay, in the book they don't assume that. Okay, and it just means that that the way you have to state things is just a little bit more precise. It has to be more technically precise. So that's the input. The output is a we'll fit it here. The output is a spanning tree T, and by spanning tree we mean it connects all the vertices. Okay, and it's got to have minimum weight. Okay, so we can write the weight of the tree is going to be, by that we mean the sum over all edges that are in the tree of the weight of the individual edges. Okay, so here I've done a little bit of abusive notation, okay, which is that instead of writing, what I should be writing is W of the edge UV, because this is a mapping from edges, which would give me a double parentheses. And, you know, as you know, I love to abuse notation. So I'm going to drop that extra parenthesis because we understand that it's really the weight of the edge, okay, not the weight of the ordered pair. Okay? So that's just a little notational convenience. Okay, so one of the things when we do the take-home exam, you know, notational convenience can make the difference between having a horrible time writing up a problem and an easy time. So it's worth thinking about what kinds of notation you'll use in writing up solutions to problems and so forth. Okay, and just in general in technical communication, you adopt a good notation, people understand you. You adopt a poor notation, nobody pays attention to what you're doing because they don't understand what you're saying. Okay, so let's do an example. Okay, so here's a graph. I think for this, somebody asked once if I was inspired by biochemistry or something. Okay, but I wasn't. I was just writing these things down. Okay, so here's a graph, and let's give us some edge weights. Okay, so there's some edge weights. And now what we want is we want to find a tree, so a connected acyclic graph, okay, such that every vertex is part of the tree, but it's got to have the minimum weight possible. Okay? So can somebody suggest to me some edges that have to be in this minimum spanning tree? Yeah, so 9, good. 9 has to be in there because why? Is the only one connecting it to this vertex, right? And likewise 15 has to be in there. So those both have to be in. What other edges have to be in?
14.
Which one?
14.
14 has to be in. Why does 14 have to be in?
Otherwise, that's not accessible. I mean, 14 and
Well, 1 of 14 and 3 has to be in there. We want the minimum weight. The one that has the overall smallest weight. So can somebody argue to me that 3 has to be in there? Yeah.
The node's only reachable by 2 edges, and that's the minimum of the 2.
That's the minimum of the 2, which means that if you had something you said was a minimum spanning tree that didn't include 3, right? And so therefore it had to include 14, then I could just delete this edge 14 and put in edge 3, and I have something of lower weight, right? So 3 has to be in there. What other edges have to be in there? Let's do a little puzzle logic.
6 and 5.
6 and 5 have to be in there. Why do they have to be in there?
The top node has to be connected to that node, to the node to the right. And 6 and 5, it either has that edge 12 or it has 6 and 5.
Yeah, well, I mean, it could be connected like through this or something. Doesn't necessarily have to go this way. But 6 definitely has to be in there for the same reason that 3 had to be, right? Because we got 2 choices to connect up this guy. And so if everything were connected but it weren't 12, I mean, 12 was in there, I could always then say, well, let's connect him up this way instead. Okay, so definitely that's in there. Still don't have everything connected up. What else has to be in there for minimum spanning tree?
7, 5, and 8.
7, 5, and 8. Why 7, 5, and 8?
Because it's less than 7, 10, 8, and 5 is less than 12.
Okay, so can we argue those one at a time? Why does 5 have to be in there? Yeah.
You could argue all 3 of those simultaneously by saying you have 4 connected components. You need at least 3 edges.
Okay, so we have 4 connected components because we have this one, oh, we actually have, yeah, this one here, and this one, good.
You need at least 3 edges to connect.
We need at least 3 edges to connect them because each edge is going to reduce the connected components by 1. Okay, so we need 3 edges, and those are the 3 cheapest ones. And they work. That works, right? Any other edges are going to be bigger, so that works. Good. Okay, and so now do we have a spanning tree? Everything is, we have one big connected graph here, right? Is that what I got? Hey, that's the same as what I got. Okay. Life is predictable. Okay, so everybody have the idea of what a minimum spanning tree is then, out of this? Okay, what's going on there? So let's, first of all, make some observations about this puzzle. And what I want to do is remind you about the optimal substructure property. because it turns out minimum spanning tree has a great optimal substructure property. Okay. So the setup is going to be we're going to have some minimum spanning tree, let's call it T. And I'm going to show that with the other edges in the graph are not going to be shown. Okay, so here's a graph. Okay, so here's a graph. Looks like the one I have on my piece of paper here. Okay. So the idea is this is some minimum spanning tree. Now we want to look at a property of optimal substructure. And the way I'm going to get that is I'm going to remove some edge UV. Move an arbitrary edge UV in the minimum spanning tree. So let's call this U and this V, and so we're removing this edge. Okay? So when I remove an edge in a tree, what happens to the tree? What's left? I have two trees left. Okay? I have two trees left. Now, proving that, that's basically one of the properties in that appendix and the properties of trees that I want you to read. Okay? Because you can actually prove that kind of thing rather than it just being obvious, which it is. Okay? Okay, so we remove that, then T is partitioned into two subtrees, and we'll call them T1 and T2. So here's one subtree, and here's another subtree. We've partitioned it. No matter what edge I picked, there would be two subtrees that it's partitioned into, even if the subtree is a trivial subtree, for example, just has a single node in it and no edges. Okay? So the theorem that we'll prove that demonstrates a property of optimal substructure T1 is a minimum spanning tree for the graph G1 E1 the subgraph of G induced by the vertices in T1. Okay, that is, V1 is just the vertices in T1. This is what it means to be induced. Okay, so V1 is the vertices in T1. So in this picture, I didn't label it. This is T1. This is T2. In this picture, these are the vertices of T1, so that's V1. Okay? And E1 is the set of pairs of vertices x and y that are the edges that are in E1, such that both x and y belong to V1. Okay? So I haven't shown the edges of G here, but basically, if an edge went from here to here, that would be in E1. If it went from here to here, it would not. And if it went from here to here, it would not. Okay? Okay? So the vertices, the graph, subgraph induced by the vertices of T1 are just those that connect up things in V1. Okay? And similarly for T2. So the theorem says that if I look at just the edges within the graph here, G1, those that are induced by these vertices, T1 is in fact a minimum spanning tree for that subgraph. That's what the theorem says. Okay, and if I look at over here conversely, or correspondingly, okay, then if I look at the set of edges that are induced by this set of vertices, the vertices in T2, in fact, T2 is a minimum spanning tree on that subgraph. Okay? Okay, we can even do it over here. Okay, if I took a look, for example, at these, let's see, what should we, if we cut out some edge like 5, let's say we cut out 5, then if I cut out edge 5, then T1 would be these 4 vertices here. And the point is that if I look at the subgraph induced on that, that's these edges here, in fact, the 6, 8, and 3 are all edges in a minimum spanning tree for that subgraph. Okay? So that's what the theorem says. So let's prove it. Okay, and so what technique are we going to use to prove it? Okay, we learned this technique last time. Hint, hint. Something you do in your text editor all the time. Cut and paste. Good. Cut and paste. Okay. So the weight of T I can express as the weight of the edge I removed plus the weight of T1 plus the weight of T2. Okay? So that's the total weight. So the argument is pretty simple. Suppose that there were some T1 prime that was better than T1 for G1. Suppose I had some better way of forming a spanning tree. Okay? Then I would make up a T prime, which was just contain the edges U, V, contain the edge UV, and T1 prime union T2. So I would take, if I had a better spanning tree, okay, spanning tree of lower weight for T1, and I call that T1 prime, I just substitute that and make up a spanning tree that consisted of my edge UV, whatever worked well for T1 prime, and whatever worked well for T, and that would be, okay, that would be a spanning tree, and it would be better than T itself was for G. Okay, because the weight of these is just as the weight for this, I now just get to use the weight of T1 prime, and that's less. Okay? And so therefore, the assumption that that T was a minimum spanning tree would be violated if I could find a better one for the sub piece. Okay? So we have this nice property of optimal substructure. Okay, I have subproblems in it that are that exhibit optimal. If I have a globally optimal solution to the whole problem, within it I can find optimal solution to subproblems. So now the question is, that's one hallmark of dynamic programming. What about overlapping subproblems? Do I have that property? Do I have overlapping subproblems over here for this type of problem? So imagine, for example, that I'm removing different edges. I look at the space of, taking a given edge and removing it. It partitions it into two pieces, and now I have another piece, and I remove it, etc. Am I going to end up getting a whole bunch of subproblems that are similar in there? Yeah, I am. Okay? If I take out this one, then I take out, say, this one here, and then I'll have another tree here and here. Okay, that would be the same as if I had originally taken this out and then taken that one out. So if I look at some ordering of taking out the edges, I'm going to end up with a whole bunch of overlapping subproblems. Yeah. Okay. So what does that suggest we use as an approach? Dynamic programming. Good. What a surprise. Yes. Okay. But yes, you could use dynamic programming, but it turns out that minimum spanning tree exhibits an even more powerful property. Okay, so we got all the clues for dynamic programming, but it turns out there's even a bigger clue that's going to help us to use an even more powerful technique. Okay? And that we call the hallmark for greedy algorithms. And that is, we have a thing called the greedy choice property, which says that a locally optimal choice is globally optimal. And of course, as with all these hallmarks, this is the kind of thing you want to box. Okay, because these are the clues that you're going to be able to do it. So we have this property that we call the greedy choice property. I'm going to show you how it works in this case. And when you have a greedy choice property, it turns out you can do even better than dynamic programming. Okay? So when you see the two dynamic programming properties, there's a clue that says dynamic programming, yes, but also it says, let me see whether it also has this greedy property, because if it does, you're going to come up with something that's even better than dynamic programming. Okay? So if you just have the two, you can usually do dynamic programming. If you only have, but if you have this third one, it's like, whoa, jackpot. Okay? Okay? So here's the theorem we'll prove to illustrate this idea. Once again, these are not, all these hallmarks are not things, they're heuristics. They're not, I can't give you an algorithm to say, here's where dynamic programming works, or here's where greedy algorithms work. But I can sort of indicate when they work, the kind of structure they have. Okay? So here's the theorem. So let's let T be the MST of our graph. And let's let A be any subset of V. So some subset of vertices. And now let's suppose that edge UV is the least weight edge connecting our set A to a complement, that is V minus A. Then the theorem says that UV is in the minimum spanning tree. So let's just take a look at our graph over here and see if that's in fact the case. Okay? So let's take, so one thing I could do for A is just take a singleton node. So I take a singleton node, let's say this guy here, that can be my A, and everything else is V minus A. And I look at the least weight edge connecting this to everything else. Well, there are only two edges that connect it to everything else. And the theorem says that the lighter one is in the minimum spanning tree. Hey, I win. Okay, and if you take a look, every vertex that I pick, the lightest edge coming out of that vertex is in the minimum spanning tree. Okay? The lightest weight vertex edge coming out. But that's not all the edges that are in here. Okay? Or let's just imagine, let's take a look at these three vertices connected to this set of vertices. I have three edges going across. The least weight one is 5. That's the minimum spanning tree. Okay, or I can cut it this way. Okay, the ones above, the edges going down are 7, 8, and 14. 7 is the least weight. It's in the minimum spanning tree. Okay? So no matter how I choose, I could make, this one in, this one out, this one in, this one out, this one in, this one out, this one in, this one out. Take a look at what all the edges are. Whichever one's the least weight, it's in the minimum spanning tree. Okay? So, in some sense, that's a local property. Because I don't have to look at what the rest of the tree is. I'm just looking at some small set of vertices, if I wish. And I say, well, if I wanted to connect that set of vertices to the rest of the world, what would I pick? I picked the cheapest one, the greedy. That's the greedy approach. Turns out that wins. Okay? That picking that thing that's locally good for that subset A, okay, is also globally good. Okay, it optimizes the overall function. That's what the theorem says. Okay, so let's prove this theorem. Any questions about this? Okay, let's prove this theorem. So let's so we have UV is the least weight edge connecting A to V minus A. So let's suppose that this edge UV is not in the minimum spanning tree. Okay, let's suppose that somehow there's a minimum spanning tree that that doesn't include this least weight edge. Okay, so what technique do you think we'll use to get a contradiction here? Cut and paste. Good. Yeah, we're going to cut and paste. Okay, we're going to cut and paste. So here I did an example to, okay, so okay, and so I'm going to use the notation. I'm going to color some of these in. Okay, and so my notation here is this is an element of A, and colored in is an element of V minus A. Okay, so if it's not colored in, that's an A. This is my minimum spanning tree. Once again, I'm not showing the overall edges of all the graphs, but they're there. Okay? So my edge UV, which is not in my minimum spanning tree, I'm saying, let's say, is this edge here. It's an edge from U. U is in A. V is in V minus A. Okay. Okay, so everybody see the setup? So I want to prove that that this edge should have been in the minimum spanning tree. Okay, that the contention that this is a minimum spanning tree and doesn't include UV is wrong. So what I want to do then is I have a tree here, T, and I have two vertices U and V, and in a tree, between any two vertices, there's a unique simple path. Simple path meaning it doesn't go back and forth and repeat edges or vertices. Okay, there's a unique simple path from U to V. So let's consider that path. Okay, and the way that I know that that path exists is because I've read Appendix B of the textbook, section B.5.1, okay, which has this nice theorem about properties of trees. Okay, so that's how I know that there exists a unique simple path. Okay, so now what we're going to do is take a look at that path. So in this case, it goes from here to here to here to here. And along that path, there must be a point where I connect from a vertex in in A to a vertex in V minus A. Why? Well, because these are in different, this is in A, this is in V minus A. So along the path, somewhere there must be a transition. Okay? They're not all in A, okay, because in particular V isn't, okay? So what we're going to do is swap UV with the first edge on this path that connects a vertex in A to a vertex in V minus A. So in this case, it's this edge here. I go from A to V minus A. In general, I might be alternating many times, okay, and I just pick the first one that I encounter. Okay, that's this guy here. And what I do is I put this edge in. Okay. So then what happens? Well, the edge UV is the lightest thing connecting something in A to something in V minus A. So that means in particular it's lighter than this edge. Has lower weight. So by swapping this, I've created a tree with lower overall weight, contradicting the assumption that this other thing was a minimum spanning tree. Okay, so a lower weight spanning tree then T results. And that's a contradiction. Okay? How are we doing? Everybody with me? Okay. Now we get to do some algorithms. Yay, okay. So we're going to do an algorithm called Prim's algorithm. Prim eventually became a very high up at AT&T because he invented this algorithm for minimum spanning trees. And it was used in all of the billing code for AT&T for many years. He was very high up at Bell Labs back in the heyday of Bell Laboratories. Okay, so just shows all you have to do is invent an algorithm. You too can be the president of a corporate monopoly. Okay, of course then government can do things to monopolies, but anyway, okay, if that's your mission in life, invent an algorithm. Okay, so here's the idea. What we're going to do is we're going to maintain V minus A as a priority queue we'll call it Q. And each vertex, we're going to key each vertex in Q with the weight of the least weight edge connecting it to a vertex in A. So here's the code. So we're going to start out with Q being all vertices. So we start out with A being, if you will, the empty set. Okay? And what we're going to do is the least weight edge, therefore, for everything in the priority queue is basically going to be infinity, because none of them have any edges. The least weight edge to the empty set is going to be empty. And then we're going to start out with one guy, we'll call him S, which we'll set to 0 for some arbitrary S in V. And then the main part of the algorithm kicks in. So that's our initialization. Okay, when we do the analysis, I'm going to write some stuff on the left-hand side of the board, so if you're taking notes, you may want to also leave a little bit of space on the left-hand side of your notes. So while Q is not empty, we get the smallest element. Out of it. And then we do some stuff. That's it. And the only thing I should mention here is, okay, so let's just see what's going on here, and then we'll run it on the example. Okay, so what we do is we take out the smallest element out of the queue at each step, and then for everything in the adjacency list, in other words, everything for which I have an edge going to from V to U, we take a look, and if V is still in our set V minus A, so things we've taken out are going to be part of A. Okay, every time we take something out, that's going to be a new A that we construct. At every step, we want to find what's the cheapest edge connecting that A to everything else. We basically are going to take whatever that cheapest thing is, okay, add that edge in, and now bring that into A and find the next cheapest one. And we just keep repeating that process. Okay, we'll do it on the example. And what we do is every time we bring it in, I keep track of what was the vertex responsible for bringing me in, and what I claim is that at the end, if I look at the set of these pairs that I've made here, V and pi of V, that forms the minimum spanning tree. So let's just do this. And look at that. We're all set up. So let's get rid of these guys here, because we're going to recompute them from scratch. Okay, so you may want to copy a new thing over in your, copy the graph over again in your text file. I was going to do it, but it turned out this is exactly the board is going to erase this. It's like, okay, well, let me just modify it. Okay, so we start out, we make everything be infinity. Okay, so that's where I'm going to keep the key value. Okay, and then what I'm going to do is find one vertex, and I'm going to call him S, and I'm going to do this vertex here. We'll call that S. So basically, I now make him be 0. And now what I do is I execute extract min. So basically, what I'll do is I'll just shade him like this, indicating that he has now joined the set A. So A is going to be, this is going to be A. And this is element of V minus A. Okay? So then what we do is we take a look at, we extract him, and then for each edge in the adjacency list, okay, so that for each vertex in the adjacency list, that's these guys here, okay, we're going to look to see if it's still in Q, that is in V minus A. And if so, we're going to, and its key value is less than what the value is of the edge there, we're going to replace it by the edge value. So in this case, we're going to replace this by 7. We're going to replace this by 15. And we're going to replace this by 10. Okay? Because what we're interested in is what is the cheapest. Now notice that everything in V minus A, that is what's in the priority queue, everything in there, okay, now has its cheapest way of connecting it to the things that I've already removed, the things that are in A. Okay? And so now I just, okay, when I actually do that update, there's actually something implicit going on in this priority queue. And that is that I have to do a decrease key. So there's an implicit decrease of the key. So decrease key is a priority queue operation that lowers the value of the key in the priority queue. Okay? And so that's implicitly going on when I look at what data structure I'm going to use to implement that priority queue. Okay, so common data structures for implementing a priority queue are a heap, a min heap. Okay, so I have to make sure that I'm actually doing this operation. I can't just change it and not affect my heap. So there's an implicit operation going on there. Okay, now I repeat. I find the cheapest thing. Oh, and I also have to set now a pointer from each of these guys back to u. So here, this guy sets a pointer going this way. This guy sets a pointer going this way. And this guy sets a pointer going this way. That's my pi thing that's going to keep track of who caused me to, to set my value to what it is. So now we go in and we find the cheapest thing again. And we're going to do it fast, too. Okay, this is a fast algorithm, okay? So now we're going to go do this again. So now what's the cheapest thing to extract? This guy here, right? So we'll take him out, okay? And now we update all his neighbors. So this guy gets 5. This guy gets 12. This guy gets 9. This guy we don't update. Okay? We don't update him because he's no longer in the queue, in the priority queue. And all of these guys now we make point to where they're supposed to point to. And we're done with that step. Now we find the cheapest one. What's the cheapest one now? The 5 over here. Good. So we take him out. Okay? We update the neighbors. Here, yep, that goes to 6 now. And we have that pointer. And this guy we don't do because he's not in there. This guy becomes 14. And this guy here becomes 8. So we update that guy, make him be 8. Did I do this the right way?
You can remove some of the pi pointers.
Yeah, because pi is a function from this guy. So basically this thing then disappears. Yeah. Did I have another one that I missed?
12.
12, yes. Good. Gets removed. Okay? Because pi is just a function. And now I'm okay. Okay, so now what do? I pick. Okay, so now my set A consists of these 3 things. And now I want the cheapest edge. I know it's in the minimum spanning tree, so let me just greedily pick it. Okay? So what's the cheapest thing now? This guy up here? Yeah, 6. So we take it, we go to update these things, and it doesn't nothing matters here. Okay, nothing changes because these guys are already in A. Okay, so now the cheapest one is 8 here. Good. So we take 8 out. Okay, we update this, nothing to be done. This, nothing to be done. This, nothing. Oh, no, this one, instead of 14, we can make this be 3. So we get rid of that pointer and make it point that way. Now 3 is the cheapest thing. So we take it out. And of course, there's nothing to be done over there. And now last, I take 9, and it's done, and 15, it's done, and the algorithm terminates. Okay, and if I look at now all the edges that I picked, those are exactly the edges that we had at the beginning. Okay, let's do an analysis here. Okay, so let's see. This part here costs me order V, right? Okay, then this part, let's see what we're doing here. We're going to do this part, well, we're going to go through this loop how many times? V times. There's V elements we put into the queue. We're not inserting anything, we're just taking them out. This goes V times. Okay, and how, then this is a constant amount of, this is, we do a certain number of extract mins, so we're going to do order V extract mins, and then we go through the adjacency list, and we have some constant things, but we have these implicit decrease keys for this stuff here. That's this thing here. Okay, and so how many implicit decrease keys do we have? That's going to be the expensive thing. Okay, we have, in this case, the degree of U of those. Okay, so overall, how many implicit decrease keys do we have? Well, we have V times through. How big could the degree of U be? Okay, it could be as big as V, order V. So that's V squared decrease U's. But we can do better down than that. How many do we really have? Yeah, at most order E. Okay, because when what am I doing? I'm summing up the degrees of all the vertices. That's how many times I actually execute that. So I have order E, implicit decrease keys. So the time overall is order V times time for whatever the extract min is, plus E times the time for decrease key. So now let's look at data structures, and we can evaluate for different data structures what the what this formula gives us. So we have different ways of implementing a data structure. We have the cost of extract min and of decrease key and total. So the simplest way of implementing the data structure is an unsorted array. If I have an unsorted array, how much time does it take me to extract the minimum element? Have an unsorted array, order V in this case, because it's an array of size V. And to do a decrease key, okay, I can do it in order 1. So the total is V squared. Good. Order V squared algorithm. Okay. Or, as people suggested, how about a binary heap? Okay. To do an extract min in a binary heap will cost me what? O of log V. Decrease key will cost me yeah, it turns out you can do that in order log V, because basically you just have to shuffle the value towards the, actually shuffle it up towards the root, okay? Or log V. And the total cost, therefore, is E log V. Good. Which of these is better? Depends. Good. So when is one better and when is the other better? Yeah.
E is close to V squared, the array is better.
Yeah, if it's a dense graph, E is close to V squared, the array is better. But if it's a sparse graph, and E is much smaller than V squared, then the binary heap is better. So that motivated the invention of a data structure, okay, called a Fibonacci heap. So Fibonacci heap is covered in Chapter 20 of CLRS. We're not going to hold you responsible for the content, but it's an interesting data structure because it's an amortized data structure. And it turns out that in this data structure you can do extract min in order log v amortized time. And remarkably, you can do decrease key in order 1 amortized. So when I plug those in, what do I get over here? What's the total going to be? Plug that in here. It's going to be v times log v plus e. E plus v log v. These are amortized, so what's this? Trick question. It's worst case. It's not amortized over here. These are amortized, but that's the beauty of amortization. I can say it's going to be worst case E plus V log V over here, because when I add up the amortized costs of my operations, it's an upper bound on the true costs. Okay, so so that's one of the, as I say, one of the beauties of amortized analysis, and in particular of being able to assign different costs to different operations, is I can just add them up and I get my worst case cost. So this is order V log V. There are a couple of other algorithms just before I let you go. Kruskal's algorithm in the book uses another amortized data structure called a disjoint set data structure, which also runs in E log V. It is this time. Runs in this time, the same as using a binary heap. So I'll refer you to the book. The best algorithm to date for this problem is done by our own David Karger on the faculty here with one of our former graduates, Phil Klein, who's now professor at Brown, and Robert Tarjan, who is sort of like the master of all data structures, who's professor at Princeton. Okay, in 1993, it's a randomized algorithm, and it gives you order V plus E expected time. Okay, so that's the best to date. Okay, it's still open as to whether there is a deterministic, there's worst case bound. Okay, whether there's a worst case bound that is linear time. Okay, but there is a randomized linear time, and otherwise this is essentially the best bound without additional assumptions. Okay, very cool stuff. Next week we're going to see a lot of these ideas of greedy and dynamic programming in practice.